to welcome Satoshi Tanda from Hokkaido, which actually has a connection to the University of Massachusetts. Our university and their university are. And linking seems to be an effective topic here. Topological crystals and quantum effects, a new paradigm.
Thank you, Chairman. Professor, thank you very much. Michael Berry, thank you. Today, I would like to talk about topological crystals and the new quantum effects as a new paradigm. Outline of my talk is as follows. First, I briefly introduce the concept of topology and show you our motivation of study. I will show you crystal growth and obtain the topological crystals such as ring, Möbius, figure 8 Hoppeling crystals. And I will show you mechanism of topological crystals. And I classify the topological crystals as well as I report electronic properties. Finally, I summarize my talk. This is the famous figures painted by Escher, 1963. He put several ants on the Möbius surfaces and returned to the original point after two laps on Möbius strips because of no distinction between the overs and reverse. Möbius strips provide an exotic one-sided world, inspired many people ranging from artists to scientists. What happens when substitute ants to electrons, spins, photons, phonons, charge density waves, and superconductor of pair, Cooper pair? What happens when substitute strips to lattice to crystals? Is it possible? What happens? Many questions inspire me for investigation of topological crystals. Our goal is, we construct topological crystallography and we observe the quantum topological effects in the topological crystals, like a berry phase. So in order to obtain the topological crystals, we propose a strategy. Goldstein and Moffat, Piquet, Pesky, and Rickson can make Möbius strip in soft film. But in the crystals, it's difficult to make a synthesize of topological crystals. Requirements. There are requirements. One is one-dimensional wire, such as protein, DNA, polyacetylene. Professor Shirakawa discovered polyacetylene. But one-dimensional wire of organic polymer is too flexible. So it is only network type materials. It's okay. So we need a second requirement as we need some fat rigidity. So we choose the inorganic polymer such as MX3, metal chalcogenide 3, metal chalcogenide 2. We choose. Inorganic covalent wires has like this figures. In the intrachain is covalent bonding, and interchain there are van der Waals weak force. Typical materials is is like this MX3. It means semi-flexible. We obtain the Foisker easily. Many remarkable researches have been done in Hokkaido University since 35 years. We obtained the ring crystals. Typical size is about 100 and to 1 micrometer, 10 micrometers. It's seamless, beautiful rings. In order to obtain the there are synthetic end condition is chemical vapor transportation. Starting materials, niobium and selenium is shielded in ample, evacuate ample. And after few weeks of heating, products are transported to the lowest temperature, and where vapor pressure is also the lowest. In order to obtain the topological crystals, we need non-equilibrium conditions. Large temperature, there are large temperature gradients in the directions horizontal and vertical. So selenium droplets, selenium circulates through the furnace, vapor, mist, liquid droplets, like Earth system. Earth system make life polymer. It's analogous method. Droplet is here. This droplet needs for formation of ring crystals. Formation mechanism is video. Video is shown. The ribbon-shaped niobium selenium crystals grown in the viscous selenium droplets and are bent due to selenium surface tension. MX3 fiber circulates on the equator of selenium droplets during growth. A growing crystal can eat its own tail. And finally, a selenium evaporate. We can get a seamless ring like this figure. Another type of ring, we obtain the tubes, disc with cone, disc with hole, UFO type, another UFO type, tube in tube, and ring crystal. Hole radius is less than 1 micrometer. It means that this system is the ideal matter in observation of interference effect of AB effect of CDW. CDW correlation length is about 5 micrometer, which is larger than hole radius. Later, I will show you. Charge density wave. Charge density wave. Yeah. Next, we obtained figure 8 crystals, like this figure. There are no evidence of breaking of chiral symmetry. And 8 figure crystal, when 8 crystal growing to these materials, it's a self-crossing maximum crystals by Hartmann-Nirenberg 7. Mechanism of formation figure 8 crystal is like this figure. Niobium selenium 3 crystal bind around the droplet 2 times during its growth and intersect with itself, and then both ends coalescence. Finally, we obtain this type figure 8 crystals. And we obtained Möbius crystals. Surprisingly, yeah, this type. In naivum selenide 3 and tantalum selenide. Mechanism of formation, formation mechanism of Möbius crystal is like this question is how the twisting is introduced without actual shear force. The answer is crystal symmetry, lower crystal symmetry. There are the bending, twisting, conversion. Bending and twisting to converge. We use the monoclinic system of crystal, naivum selenide 3, and shear bending to convert to twisting. This is the evidence of twisting like this figure. Formation of maybe crystals is shown like video. To form a maybe strip, a twist is needed to be introduced during the spooling. So, can we introduce the concept of topology into crystals? Originally, what's crystal? The answer is black reflection by definition of International Union of Crystallography, 1991. Snow crystal has a black spot like this figure, and quartz crystals has a 5-fold symmetry like this figure. And topological crystals, what? We measure the X-ray diffraction patterns like black ring. Line is homogeneous. It means single crystals. So I categorize of I will classify of topological crystals. Omega is wedge disclination, and omega star is twist disclination, distillation. In the case of conic crystals, omega equal 1/2 pi, omega star equal 0. In the carbon nanotube, omega equal 2 pi, omega star 0 pi. Omega star and omega is independent usually due to topological defect theory of crystal as yet. I propose a new definitions of by use the not 2 pi 0 pi, 2 pi 1 pi, 2 pi 2 pi. Its linking is 1. So we discovered the Hoppening crystals. Hoppening crystals cannot be categorized by the linking number of knot crystals and the usual point groups. We need a new classification. So we propose the embedding manifolds, ring to sphere, Möbius to Kleinbot, 8-figure crystals to torus, and finally Hoppening to mapped embedding double torus systems. We propose a new classification with embedding manifolds. So we categorize of crystal. We propose a category of crystals. Solid, translational symmetry. Crystal has a translational symmetry. And quartz crystal has a 5-fold symmetry and incommensurate structure. and we observe the topological crystals. Topological crystal synthesized by polymer. It's important. Professor Kuroto suggests me the onion crystals in the topological group. Anyway, next we show the quantum topological effect in the topological crystals. Diamond selenide 3 has take place charge density wave transition, electron to macroscopic wave function. Take place at 145 Kelvin and 52 Kelvin. And charge density wave can sliding without friction. Atom is only oscillate, but macroscopic quantum, macroscopic wave function is sliding. It is called Friedrich superconductor. In the loop crystal, in the case of CDR loop, eternal current should appear, emerge. We observed Shapiro peaks in CDW loops. We used the ring crystals and applied field, applied AC current. We obtained the sub-peaks at both sides of main peak, like this figure. We analyzed peak positions. All data, closed circle is show the main peak, and satellite sub-peak is empty circle. And all data fall into 3 lines. We discover the beat peak only in the loop CDW. And additional current must exist in the loop CW, like this. We estimate the damping time of circulating current. If charge density wave is circulating, the damping time can be estimated by circumference 10 minus 4, phase on velocity 10 4, circumference by phase on velocity 10 minus 8. It means naive selenide 3 phase on damping time is less than 10 minus 11. It's elogantation of damping time. It means a precursor of Friedrich supercurrents. Next, we observe the AB effect of charge density wave. We use the ring crystals and we electrode like this figure. And we obtained oscillate peak. Periodic oscillation was observed. And we estimate of a unit charge. Unit charge corresponds to 3. And recently, we observed a quantum coherence at temperature of liquid nitrogen, like this. We also observed liquid temperature, liquid nitrogen temperature. We propose a quantum phase slip model in charge density wave, applied field and phase slip and periodicity h/2e. Finally, I propose application of topological crystal. Niobium S3 ring crystals take place room temperature have room temperature macroscopic wave function. In future, we obtained room temperature split like this. So topology defines the properties of condensed matter ring to cut ring. In the case of cut ring, we obtained cycloid type, cycloid crystals, and insulator and superconductor, amorphous lattice, and cylindrical vortex. I also many field applied many field. I will. Thank you for your attention. Buddhist, Japanese Buddhist Hakim explaining Zen by using maybe sleep in 1785. Wow.
More Buddhist. Again.